on to our last panel speaker. So thank you, Mirko, and I'd like to introduce Professor Oliver Brock from TU Berlin, where he leads the RBO lab in Robotics and Biology Laboratory, with work ranging from manipulation and sensing through to protein structure prediction. So Oliver, can you hear us okay?
I can hear you. Can you see my slide? Yeah, perfect.
Excellent.
All right, we're ready to go. That's great. And I realize that I'm what stands between us and the most interesting part, which is the discussion. So I'm going to try to be concise. Yeah, my name is Oliver Brock. I'm part of the Robotics and Biology Laboratory, but also of this large research center called Science of Intelligence, which is very much trying to deal with the definition of intelligence, which Rebecca in her talk, which I really appreciated a lot, was also trying to attack. I'm going to try to talk about embodiment as a computational paradigm, and in the process, try to understand what really we mean by embodied intelligence. What you see here is a quantum computer, and I think we all are aware that there are things that quantum computers can do that other normal von Neumann type computers cannot do. For example, factorize large integers. So I would like to, I'm showing you this to make the point that in a different computational paradigm, a problem that's not solvable in another one might be solvable, right? So if you had to factorize a large number into its prime factors, you should use a quantum computer, and it would be hopeless to use one of the traditional computers that we're using to speak to each other. I want to show you another example, which maybe leads us to another computational paradigm. What you see here is the site of the 1974 Olympics. I'm going to zoom in on the right part of this. The roof structure that you see here was considered an architectural sensation back then, mostly because back then people didn't have computers to compute these structures. So how did they do it? Well, they did it by actually taking sticks and taking nylon stockings and then sort of pushing those nylon stockings over those sticks. I didn't find a picture of this particular structure, but here's a very poor picture of a small architectural model where exactly this has happened. So the idea is that in these nylon stockings, there seems to be a kind of computation locked up that is maybe reminiscent of soft robotics, of morphological computation, of embodied intelligence, that was not available on the computers available in the 1970s. Still today, architects actually prefer to work like that, and then only when they kind of are done, move to high performance computers to simulate things like the one that you see here. So what's behind this? Is this really an additional computational paradigm? Well, let's take a look at the simplest possible example, which is kind of this cube here of material, and it's discretized just for the sake of discussion. Let's assume that I'm applying some kind of force here, right? I could actually sense the effect of these forces at different places on this structure. And all of this happens, the force is being propagated through this cube with the speed of light, with the speed of sound. We could actually modify the computation that's going on here by taking one of those cubes and replacing the material, changing the shape of the overall cube, or even putting actuation into one of those little cubes, right? So I would argue that we actually do have a different computational paradigm here, and I'm going to try to argue that by comparing it to von Neumann type computation. I think, as was mentioned earlier, I think the answer is that the other paradigm really should be called morphological computation. Now, let's call this length L of the cube. If we want to do some kind of finite element analysis to compute how the forces propagate, it would be at least a cubed operation. If we want to do it in this morphological computation paradigm, it's a linear operation. We need a specific model, and we don't need anything on the morphological side. And this is an approximation versus reality, right? We would actually have to compute friction models and so on and so forth. So this is an example, I think, a very simple example of something that is very, very difficult to do under von Neumann computation, at least to do precisely, and that is trivial to do with morphological computation. So I would argue that this is really a different computational paradigm compared to the things that we're used to. Well, the question becomes, how do you program such a cube? And we've tried to do that by programming a hand. Here you see this hand, and Aditya gave a talk about this yesterday in one of the breakout sessions, rotate with the exact same actuation command 8 different kind of shapes, different weights, different shapes, different surfaces. It's the same command that is executing on all of these hands, and it's rotating all of these 8 objects. So where does this difference come from? Well, it must be computed by the hand. And I want to show this to you in a more detailed example. So you see here 2 actuators, the middle bellow and the thumb tip, that are actuated. Nothing else is actuated in the video that you're about to see. On the bottom, you see the actuation level, and only during the first half second, actuation changes. After that, everything you see after that is playing out by itself, by kind of the morphology. So now actuation is finished, and everything you see now is basically computed and controlled by the morphology. So this is behavior that originates from the morphology, and that basically is not driven by any kind of computation in the von Neumann sense. The people that are involved in this are Aditya Bhatt, who gave the talk yesterday, Adrian Siele, and Stefan Puhlmann. So this is one example. I want to show you another example of how computation that is morphological can actually be leveraged in interesting ways. So here, let me just play some sounds. So here you see the cut open finger. This is a pneumatic actuator. One of the walls is cut open. So we're seeing the inside, the chamber that is supposed to be actuated. What you see here is a speaker. And here, this part here actually is a microphone. The rest is power electronics. So the speaker emits some sound that then gets sort of transmitted through the material and then emitted back to the microphone. But what happens here is that the sound gets modified by the morphology in response to if there is something contacting that part of the morphology. And actually, so you can detect, then you record the sound and you can analyze the sound using computation, and you can reconstruct what the interaction of this finger was with its environment. You can reconstruct temperature, you can reconstruct contact location, you can reconstruct contact forces, and many, many other properties that are all embedded into this modulation of the sound signal as the morphology transmits it. So we have a sensor that is not even really sort of designed for any particular type of sensing, that just senses changed state in the finger, and you can reconstruct all kinds of different properties. So it's kind of a very generic sensor. We've not really found many things that you cannot reconstruct from this sound. So again, this is something that we couldn't do with other computation. We're leveraging here the fact that the entire body is performing a modulation, you can call it a computation, of the sound signal. It's encoding its own state in this sound signal. So this is, I guess, another example, I would argue, of how we are entering a completely different paradigm that affords entirely new opportunities. The people that are involved, this is sound, you probably cannot hear this because I didn't turn the sound on. But the people that are involved in this are Vincent Wall, Gabriel Zöllner, and Marius Hebecker. So going back to the question of embodied intelligence. The Stanford Encyclopedic Dictionary of Philosophy defines embodied intelligence or embodied cognition as embodied when it is deeply dependent upon features of the physical body other than the brain. So we're kind of taking the brain and we're separating ourselves, and we're saying everything that is not the brain is embodied intelligence. Well, this is, I think, a remnant of dualism, right? Of really thinking that the mind and the body are separate things. Obviously, the brain is also part of the body. So we are making up this dichotomy, which I think is an old dichotomy of brain and body, and all of this dichotomy doesn't survive to our synthetic domain. Obviously, a robot doesn't have a brain, so this distinction kind of becomes strange. And so I would like to propose a different distinction, I would like to say that intelligence, whatever that is, it's very difficult to define, but that what we're talking about is the combination of multiple computational paradigms. And that what we call embodied intelligence is the combination of morphological computation and this traditional memory-based and algorithmic logic unit-based computation. And I think that by articulating it like this, it becomes clear that we need to understand morphological computation at the same level that we understand normal computation. We need to have, the corresponding disciplines like complexity theory, and we need to understand what the right programming paradigms are, like object-oriented programming and so on. I don't know what they will be in the context of morphological computation, but I think we need to recognize that what we mean by embodied intelligence is really combining these different computational paradigms to our advantage. And I think to achieve intelligence, it is even necessary to do that. So with that, I'm going to close, and I'm very much looking forward to the discussion.
Thank you very much. I think that's a fantastic message to start on. I think we can start our discussions from there.